Welcome to the next session, my dear friends. So in the previous session we are discussing about the air pollution. So we have studied what are the different kinds of pollutants, classification of the pollution, all those things we have seen. So in this session we are starting with the finding the concentration of the pollutant. Okay, so concentration generally in water supply or wastewater, we expressed the concentrations of the impurities in mg per liter or ppm, parts per million. So that parts per million or mg per liter, we cannot use it here because we cannot define volume for air or gas. Okay, so that is why generally what are the units which we use here. So what are the units generally which we use here are, so microgram, so the pollutant, the pollutants of air is represented with microgram per meter cube. Okay, so microgram per meter cube or ppm, parts per million, and parts per billion, but not these parts per million, parts per billion is not same that in the water supply or wastewater. It is different here. Let us see what is difference here. See, generally we use for these kind of pollutants or air, we use a equation, an important equation, that is universal gas law. Using the universal gas law states that PV is equal to nRT. So this you might have heard so from your schooling itself. So there is an equation. So this is universal gas law, PV is equal to nRT, where n is the number of moles. Okay, where n is number of moles. For 1 mole of gas, we can write this as PV is equal to RT. PV is equal to RT. So V is equal to, from here I can write this V is equal to RT by P, where R is universal gas constant. Universal gas constant, and its value is equal to 82.05 into 10 to the power of minus 6, 82.05 into 10 to the power of minus 6 atmosphere meter cube by mole because R is equal to PV by RT. So P unit is atmosphere, V unit is meter cube, R unit PV by NT. So N unit is mole and this is degree centigrade, and T unit is degree centigrade. So the unit of R will be coming from these four: atmosphere, meter cube, mole, and degree centigrade. Now this is a fixed value for any gas. This is a fixed value. Now if I fix this temperature and pressure also, I call that as at standard temperature and pressure, at STP, that is standard temperature and pressure. At standard temperature and pressure. Standard temperature is how much? 0 degrees centigrade or 273 Kelvin. So that is standard temperature. Standard pressure is 1 atmospheric pressure, that is natural pressure. that is 1 atmospheric pressure. If I give the standard temperature and pressure, and R is constant, now STP is also constant, so that means every gas, so this is for any gas, so for any gas volume is independent on its gas property. So we don't need the density of gas, we don't need the type of gas present in the air. So any gas will occupy the same volume at standard temperature and pressure. Okay, any gas occupies a same volume at standard temperature and pressure. That is, volume of any gas at STP is equal to 82.05 into 10 to the power of minus 6. Okay, so 1 mole of any gas, 1 mole of volume of 1 mole. So volume of 1 mole of any gas at STP. So 10 to the power of minus 3 atmospheric pressure meter cube by mole degree centigrade multiplied with 1 mole. Temperature is 273 Kelvin, that is 1 degree centigrade only, and atmospheric pressure, that is 1 atmospheric pressure. So if you do this, we will get the volume in meter cube, which is equal to 22.4 into 10 to the power of minus 3 meter cube. If you solve this, we will get it as 22.4 into 10 to the power of minus 3 meter cube, which is nothing but 22.4 liters also. Okay, we can call it as 10 to the power of 22.4 liters also. So any gas at standard temperature and volume, temperature and pressure, 1 mole of any gas having a volume of 22.4 liter. Okay, so that means 1 mole means 1 mole means m grams of, so 1 mole means how much weight? Some molecular weight. Let us take, because irrespective of any material, any gas, we are taking the same volume. So what is the weight of that 1 mole? That means it will be having the molecular weight. Let us take this as m grams. So m grams of any gas at STP will have a volume of 22.4 into 10 to the power of minus 3 meter cube. Okay, into 10 to the power of minus 3 meter cube. Then 1 gram. Then what is the weight of, what is the volume? We want it in microgram per meter cube. So 1 meter cube of any compound will weight. So for 1 meter cube it should be equal to m by 22 m gram by 22.4 into 10 to the power of minus 3 meter cube. Okay, so 1 meter cube of any gas at STP weighs m by 22.4 into 10 to the power of minus 3 grams per meter cube. So this is the weight of 1 meter cube gas. This is the weight of 1 meter cube gas. So 1 parts per million. What is 1 parts per million? What is the 1 parts per million? That is 1 part of any gas by 10 to the power of 6 parts of air. So 1 part of any gas by 10 to the power of 6 parts of this is nothing but 1 ppm. This is nothing but 1 ppm. So 1 part I will take here 1 meter cube. So instead of part I take it as 1 meter cube of any gas. Okay, I take it as 1 meter cube of 1 meter cube of any gas by 10 to the power of 6 meter cube of air. 10 to the power of 6 meter cube of air. I will take it like that. Now that is nothing but 1 ppm. So 1 meter cube means what? 1 meter cube of any gas means what? This is 1 meter cube of any gas. Okay. So now what I will do? 1 meter cube of any gas is nothing but 1 ppm is equal to 1 meter cube of any gas is nothing but this m by 22.4 by 10 to the power of 6 by 10 to the power of 6. By 10 to the power of 6. So what this is coming? M by 22.4. This gram I will convert it into microgram. So if I am converting this gram into microgram, then it will become 10 to the power of 6. 10 to the power of 6 microgram. 10 to the power of 6 microgram. So which is equal to m into 10 to the power of 6 microgram by 10 to the power of 6 microgram by 22.4 into 10 to the power of minus 3 meter cube m into 10 to the power of 6 microgram 22.4 10 to the power of minus 3 into 10 to the power of 6. So this 10 to the power of 6 will also become the denominator. Okay. So this 10 to the power of 6, this 10 to the power of 6 will get cancelled, which is equal to m by m. This 10 to the power of minus 3 goes up. Microgram per meter cube. Microgram per meter cube. See, listen again. So what I have did is simple. PV is equal to nRT. N is I have taken as 1 mole. PV is equal to RT. V is equal to RT by P. R is universal gas constant. Which value is this? And standard temperature and pressure. I am T by P. Very, very important. T by P is the multiplication factor which I am using to derive this V. This is the key point. Because if I am not taking this T by P as standard temperature and pressure, then 22.4 will not come. Why this 22.4 is coming? Because I am taking this T by P as 273 and 1 atmospheric pressure. In the examination, the changing will be there at this point only. So they won't give you temperature and pressure as standard temperature and pressure. They will give different values of T and P. So if T and P changes, which one will change? This will change. 22.4 will change. So that is the only type of questions which we can expect. So they will change T by P. So T by P if changes, then V changes. So T by P is the correction factor, multiplication factor which we are using to find the volume. So here standard temperature and pressure I am taking, that is why it is 273 and 1 atmospheric pressure. If I multiply it here, then I am getting this V as 22.4 liter. 22.4 liter. Okay, keep it aside now. So 1 mole means m grams. So 1 mole of any gas at STP is having a volume of 22.4 liters. That means m grams volume is 22.4 liters. So 1 meter cube. So if I want what is the mass of 1 meter cube, then 1 meter cube should have a weight of m by 22.4 into 10 to the power of minus 3. Okay, so you can take meter cube here, we can keep it here, anywhere you can keep. So this is the gram, this is the weight of 1 meter cube gas. This is the weight of 1 meter cube gas. So 1 parts per million is 1 part of any gas by 10 to the power of 6 parts of the air. So 1 part I will take it as instead of part I am keeping meter cube here, and here also 10 to the power of 6 meter cube I am taking. So 1 meter cube of any gas will have a weight of 1 meter cube of any gas will have a weight of m by 22.4 into 10 to the power of minus 3. This is the 1 meter cube's weight of any gas. So by 10 to the power of 6. So this gram I am converting this into microgram, that is I am multiplying it with 10 to the power of 6. So 22.4 10 to the power of minus 3 remains same. This 10 to the power of 6 will go as a denominator, that is again 10 to the power of 6 will come here. So this 10 to the power of 6 and this 10 to the power of 6 will get cancelled. So m into this 10 to the power of minus 3 will go up. So m into 10 to the power of 3 by 22.4 microgram per meter cube, this is equal to 1 parts per million. So 1 parts per million is nothing but one parts per million is nothing but m by at standard temperature and pressure. At standard temperature and pressure, is equal to m into 10 to the power of 3 by 22.4 microgram per meter cube. Similarly, 1 microgram per meter cube at standard temperature and pressure is equal to 22.4 by m into 10 to the power of 3 ppm. 22.4 by m into 10 to the power of 3 ppm. Similarly, 1 ppm at any temperature T at any pressure P is equal to, so m into 10 to the power of 3. Here this constant will not be 22.4. Here this constant will not be 22.4. So there will be different constant that will come. By constant. Similarly, 1 microgram at any temperature and pressure T and P is equal to constant by and here 1 parts per billion 1 parts per billion is equal to, so parts per billion means million is 10 to the power of 6, billion means 10 to the power of 9. So if I divide it with 10 to the power of 9, so this 10 to the power of 3 will also go. Okay, so this is already ppm. So by ppm by 1000, 10 to the power of 3, that is ppb. So here also I will do divide it with 1000, then it will become m by this is 1 ppb at standard temperature and pressure. Similarly, 1 microgram per meter cube at STP is equal to 22.4 by m ppb. 22.4 by m ppb. Okay. So similarly here at any temperature 1 ppb at temperature T and pressure P is equal to m by constant and similarly 1 microgram per meter cube at any temperature T and pressure P. Then what is this constant? So everywhere I am writing it as constant. What is that constant? That is not 22.4. So the constant is nothing but volume, which I have defined using T by P multiplication factor. So that is nothing but 82. So T by P into 10 to the power of 3, because it is how much? 22.4. So I have taken separated this 10 to the power of 3 out of this. So that is why the constant is nothing but simply, so 22.4 I am taking. So I am taking it as 22.4 only. So that is why I have to multiply it here with 10 to the power of 3 multiplication factor. Okay, that is 10 to the power of minus 3 into 10 to the power of 3, 82.06 into 10 to the power of minus 6. So this is the constant value, 82.05 into 10 to the power of minus 3. T by P is the constant value. So you have to use this formula. What is the temperature in Kelvin and pressure in atmospheric pressure? Temperature in Kelvin and pressure in atmospheric pressure. So if you substitute that, we will get the constant value. T in Kelvin and P atmospheric pressure. These are the units. So these formulas, whatever the formulas I have written here, so they are all very, very important for the GATE examination. They are all very, very important for the GATE examination. Many questions, 2 marks questions are coming from these concepts only. Okay, the only numerical 99% probability is there to get from this topic, that is this concept only. Very, very important concept. So now let us now discuss pollutant, each and every pollutant, major pollutants in the atmosphere, and we will discuss the pollutant and how we measure it and what are the problems associated with that pollutant if it is present in excess. So the major pollutants, first and foremost important air pollutant is particulates. So the particulates are the very, very important pollutants. So these particulates are nothing but small matter. So very small matter like dust. So every day we see the dust. Okay, small precipitates of water droplets. Okay, all these things are natural or anthropogenic particulates. What are being generated? Dust is a natural aerosol or particulates, and water droplets is a kind of another kind of it may be natural or man-made. So these are all different kinds of particulates, generally having a size ranging from 0.01 micrometer to 200 micrometer. So all these things are called particulates. All these things are called particulates. Okay, so we measure them in the form of total suspended particulates. Okay, we measure them in the form of total suspended particulates, that is TSP, or we measure it as suspended particulate matter. Suspended particulate matter. SPM. Either we measure it in the form of TSP or we measure it in the form of SPM. Both are same. So we can call them as TSP or SPM. So what they cause is majorly they enter into the mucus. So when we respirate the air which is having more suspended matter, particulate matter, so it will cause irritation. So it will directly enter into the nasal tract and causes irritation to the respiratory system. Okay, it causes irritation to the respiratory system. And causes respiratory diseases So these particulates, okay, so these particulates are generally, I told you already, it may be water droplet or it may be a solid dust. So generally they are classified as solid particulates and liquid particulates, they will be present. And when the diameter is very less, though solid or liquid, we call them both as aerosols. Okay, so when the diameter is very less, so both solid and liquid, we call them aerosols when the diameter is less than 1 micrometer. When the diameter is less than 1 micrometer, so solid particulates, generally the dust, okay, and the smoke, fumes, all of them, smoke, fumes, fumes, fly ash, etc. All these are solid particulates. Liquid particulates are water droplets. Okay. And again in aerosols also same thing will come, but in a smaller diameter, and the size is less than 1 micrometer. Then the same solid and liquid particulates will come here also, but we call them as aerosols. We call them as aerosols. So how to determine? So how to determine these aerosols? How to determine these aerosols? Generally these aerosols we determine using high volume air sampler. So they are estimated using high volume air sampler. Okay, high volume air sampler we use to find the concentration of particulates present in the water, in the air, in the air. So here what we do is we will send the air through a filter paper. So there will be a filter paper. So we will allow the air to pass through this filter paper. Okay, so we will allow this air to pass through we suck the air. We suction, by suction what we do, we will suck the air using a suction pump here. So here we will use a suction pump. So this suction pump will suck the air. So the surrounding air will enter through this filter paper and we will send out the air. So this is the air in and this is the air out. So we suck it and we send it into the outlet pipe. So we do it, it's a continuous process. So here after some time we will find the weight of this filter paper. So the total suspended particulate or suspended particulate matter in microgram per meter cube, which is equal to so initial weight and final weight. So the initial weight of the filter paper and final weight of the filter paper is recorded, and the difference is nothing but the particulate matter which is entrapped on this filter paper. Okay, so that we can find by taking the difference. So weight final minus weight initial of the filter paper, it will tell us how much particulates are entrapped on the filter paper. How much particulates entrapped on the filter paper in microgram, and what is the total volume of air you have sampled. So what is the total volume of air you have sampled? That is volume. So volume of air sampled. So that is volume in meter cube. So we will get this as microgram per meter cube. So this is how we find the total suspended particulates or suspended particulate matter in microgram per meter cube. So likewise generally we do. How to control this? This is particulate is an impurity. So we will discuss it later how to control this. So far we have discussed. So what is the effect of this on human beings or any other living beings or even monuments and all we will discuss. So that is we have discussed, and what are the basic classification of it, how to estimate it. These things we will discuss for other pollutants also. So next important pollutant, that is carbon monoxide. Next is carbon monoxide. Next pollutant is carbon monoxide. So these carbon monoxide, whatever be the carbon monoxide, so that comes out of the incomplete combustion of hydrocarbons. Okay, so it comes out of the incomplete combustion of So it comes because of the incomplete combustion of the hydrocarbons. Actually, this is an inert gas only. So it is exhaust due to incomplete combustion of which is highly poisonous if enters into human body. So generally, so if it enters into the human body, then it is very highly poisonous. We call this as asphyxiant. Okay, so we call this as asphyxiant. So when it comes into the body, generally this is an inert gas, it is stable gas. Okay, CO, it is a stable compound. It is a stable compound outside. It is a stable compound outside. But if it enters into the body, this carbon monoxide will react with hemoglobin present in the blood. Hemoglobin present in the blood, and it forms carboxyhemoglobin. It forms carboxyhemoglobin. So it forms carboxyhemoglobin, so which changes the viscosity of the blood, because of which, so the blood clots. Okay, so that it causes some kind of blood clots and all, and it also causes respiratory problem. You feel like you cannot feel fatigue and breathlessness. We call that as asphyxia. Okay, we call that as asphyxia, that is breathlessness. So it causes asphyxia. That is why we call this as asphyxiant. So carboxyhemoglobin is asphyxiant, okay, which causes this asphyxia. Okay, so that is why higher concentration may also causes death also, fatality. So higher concentration of COHB leads to fatality, that is death. Above 1000 ppm if it goes, okay, then it causes even death also. It is analyzed using NDIR technique. So it is analyzed using NDIR technique, that is non-dispersive infrared analyzer. NDIR infrared analyzer we use to estimate the carbon monoxide. Okay, So this is the second major pollutant. So rest of the major pollutants, the SOx, NOx, hydrocarbons. So all these things we will discuss in the next session. Thank you so much.